computer. And now share my screen. Okay, and minimize this. There we go, because I want that out of the way as much as possible. Okay. Yes, I know participants can see my screen. That's kind of the way screen sharing works. Okay. So, all right, so welcome. This is 1051. I love teaching this class. This is the class that is Intro to Programming in Python, but you probably already knew that based on the fact that I've got this up on the screen and it's over here as well, and it's on your schedule saying Intro to Programming in Python. I think you can also guess what the subject of the course is based on the name. But really, it's a fun course. But who is it for? And the answer is everybody. We have a pretty diverse range of students in this course. Not all of you are computer science majors or IST majors or data science majors. A lot of people are from bio and neuroscience. A lot of people are from engineering. A lot of people are here just because they want to get some programming experience or see if it's right for them. There is a broad range of students who are taking it for a variety of reasons. Some people aren't sure what they want to do. Some people are pretty sure what they want to do. And some people just want some programming before they get out of the, before they get out of this, out of the university. So I had to close that. So today, primarily, we're going to go over the syllabus and also talk about a bit the history of what computer science is versus what it isn't versus what programming is. The objective of our first week is to make sure that you get up to speed and set up with Python on your computer. If you don't have a computer or a device, you should come and talk to me. And by computer, I mean, something that's bigger than a phone. A tablet will most likely work. I'm pretty sure there's Python interpreters that run on both iOS and Android, as well as editors. But, I'm partial to laptops. This is because we do a lot of exercises, a lot of programming exercises in class. And I'm going to take the moment to point out to everybody here, because this is not necessarily something you'll know unless you actually, spend time actually like looking at your chairs. This black bar underneath your chair, by your feet, that's the power bank. There's power plugs in that. So you can plug in your laptop over there. And also in other large lecture halls, a lot of the larger lecture halls, like the one in, I think, Bury, the power sockets are actually underneath the armrests. A lot of so take a moment to check out your, seats, because surprisingly, a lot of them have power here. All right. So without further ado, I think I've stalled long enough for people to get here to go ahead and start going over this over. All right. So I'm Professor Andrew Rosen. I've been teaching CIS 1051 here for a while. I teach basically all of the sections except for one of this course. I also teach 2168. So if this is Computer Science 1, then I also teach Computer Science 3 as well. I also am the advisor for the data science programs here, as well as the 4+1 master's, bachelor's and master's program, as well as the Math CS joint program and the CS Physics joint program. So I wear a lot of hats. So if you have questions not just about programming, but also like the curriculum in general, I'm more than happy to answer those questions for you. So I went ahead and put the most important points on the first page for everybody, because the amount of stuff I have to add into the syllabus that the university mandates makes the syllabus rather long. So the important points here. This is a partially flipped class, meaning that you will read and watch lectures and material each week before coming into the lesson sessions where we actually do some practical exercises in them. As far as the textbook, it's free, because who wants to pay for textbooks? It's a free online textbook. I'll get into that in a bit. Labs are going to be held in person unless otherwise specified, like the TA has to cancel lab for a reason. The Zoom link, hyperlink here, Discord link, and lecture recordings are on the front page of Canvas. So you can find links to all these lectures that I'm doing right here. You can find them here, as well as a link over here. My YouTube channel, which is also where I post that. You can find that directly over here. And the Discord that I have for class. I have a Discord set up for this class as well as all the other classes. It's the same Discord I use each semester. The reason for this is that a lot of students come in and they'll socialize with other students and they'll exchange contact information and form their own study groups, which is great. But if you join like, a couple days later, you miss out on all that initial stuff. You don't get looped into a lot of the, group chats and stuff. So I've made a space to facilitate that. There's also plenty of students there. It's fairly active from previous semesters. So it's a great resource. It also is a great way to get quick responses from me because because whereas typing yes or no is appropriate on Discord, but like on an email, that kind of just feels rude to just simply have a one-word response in email. So anyway, turning in your homework. In this course is a two-part process. To submit your homework, you upload the appropriate files to Canvas. Homework is judged late based on the day it's submitted and not when you demo it, which is the next portion. To get your credit for your homework during lab or office hours with either me or the TA, you show us your work. You run it for us and you answer a few questions about it. This is to make sure, you actually know what you're doing here, as well as it's essential for later programs to show us that, that you wrote your own code. Homework not demoed by the end of the semester becomes a 0. I will remind you multiple times about demoing it. It's not as strenuous as it seems. I mean, you're supposed to be going to your labs. You'll have plenty of time in lab to demo your assignments. And again, we're fairly flexible about when you demo them. I'll get into that. That being said, uttering some variation of, I didn't know we needed to demo our assignments to receive credit after the first exam will be grounds for an instant 0 in the course for failing to read directions, a problem that has lethal consequences in programming. I used to get this all the time, by the way, and suddenly when I put this clause in the front page of the syllabus, nobody emails me that anymore. So it's worked wonders now. So your textbook is here, runestone.academy. There's a lot of different textbooks, and our course will use this code. So that's how you sign up. When you sign up, you want to use your TU email as your email. So whatever, TU something, 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 not your alias, but your actual TU email. Also use your name as displayed on Canvas as your name. As long as one of those two things are used, then I will then my script will automatically be able to grade you and import those into Canvas. Otherwise, I have to like manually pull your grades in, and that's a time-consuming process. So, oh, I didn't remove this sign. We aren't signing up for office hours anymore. We're just holding office hours like normal now. Don't cheat. I'm pretty good at catching cheaters. Pattern matching is a subdomain of computer science. Writing a plagiarism detection program is not unreasonable for students in CS2 or CS3. So the courses that follow this. I have made 56 charges against students since fall of 2021, and all of them have stuck. And I don't charge unless I'm 100% sure that cheating occurred. So, and don't come to class if you're feeling sick. Even on exam days, I will work with you to make it up. And of course, I record the lectures, so you'll be able to catch that. Okay, so this is introduction to the disciplines of computing and programming. It is designed for people who are completely new to programming, and those who do have some experience. So if you already know a lot of this stuff, don't worry, you aren't going to be completely bored in this class. And for those of you who are completely new, don't worry, I don't want to stress you out too much this semester. I want this to be, fairly comfortable experience, but at the same time, I do warn you that the first 4 weeks week 1 and 2 give a bit of an impression about as far as the speed of the class goes. And then the important content starts coming around 3, 4, and 5. So if you can do weeks 3, 4, and 5, well, then you're clear for this course. You're not going to have a problem with it. So the idea here is that I want to give you a sufficient amount of, if you're not going to computer science, I want you to give you enough programming know-how that you can do quite a bit to help you with whatever task you want, be it whether you're in a science like biology, or you're going for more of a business program, or you're going into something like actuarial sciences, or maybe your job is just going to be working with spreadsheets all day. Sounds not exciting, but it's fair. But if programming can take a job that takes hours and reduce it down to something that takes, minutes, that's great. So it's a 4 credit hour course, 3 lecture hour, 1 lab hour. So that means, based on the way that, these things are judged at universities all over the US, that means you're expected to spend 8 to 12 hours on coursework each week outside the lecture. Computer science is a skill-based course. The best comparison I can make is not to mathematics, which is the common comparison, but to a language class or to a music class. You don't have a you don't have a good time in those classes if you don't practice. And certainly you can't perform in music if you don't practice. Time and place, I'm obligated to put this in the lecture right here, even though you've managed to find it, even though it's on your schedule. So courses may be held over Zoom if I'm sick, or, we're completely snowed out. All the labs are either on Monday or Friday, which is really convenient. So you have signed up for 1051 dash and then either 1001, 002, 003. That's your lab. Your lab is already on your schedule. I just have to list them all here as per the requirements. Follow what's on your schedule. Prereqs, math and C in 1021. Basically, I want you to know what the Euclidean plane is, the 2D plane, the one you've been working with since you actually were introduced to graphs. As long as you know what the 2D XY coordinate plane is, then you're going to be fine as far as math is concerned. Okay. So a reliable laptop is strongly recommended, especially since I'm going to be using an online textbook. If using your computer is a painful experience, we need to talk, because you're going to suffer. And I put a lot of detail into the kind of suffering you're going to be having this semester if using your laptop's a painful experience. Worst case scenario, go out to one of the kiosks. I think there's one in the engineering building over there. There's kiosks with laptops all over the campus. You can borrow them for up to 4 hours. Your textbook has an online Python interpreter that you can use, and that will work up until week 7. And then week 7, we have a file reading assignment where that's less useful, but for getting the basics down, and until we can figure out a technology situation that works for you, that's fine. So again, there is all this stuff about that I had to put in from COVID about there's resources available, but in general, you can get away with getting a laptop for around $450, and that will last you from freshman to senior year. I got a laptop. I did all of my grad school work on a $450 laptop, and I still use that laptop, not this one, but I still use it at home for various tasks. It works. Okay. Again, our textbook is free. This is the information here. I'll go into that in a bit. But you can, but if you find that you need something on paper because you need physical paper, here are 2 resources that are also free online that you can print out, or you can buy a hard copy of it for 20 to 30 bucks, because again, textbooks shouldn't cost that much. Okay. And finally, Python has their own official documentation and tutorial that I've linked here. All these are hyperlinks you can click on. Office hours. Hopefully by now, since this is your second semester for most of you, you know what an office hour is. That is where I have set aside time to meet with you. No appointment necessary. Just walk into my office and bug me. So my office is in so this building, 349, so 3rd floor. My office hours are currently 12:30 to 1:30 on Tuesday, Thursday, so right before this class. If that does not work for you, and I know for some of you that does not work for you because you probably have class during that time, I also will do office hours over Zoom in the evening by appointment. So just send me an email and we'll just coordinate a time and I'll meet with you. Don't worry about meeting me too late. I typically get in bed around 11 o'clock. So as long as we are, so as long as it's before then, I am more than happy to meet with you. Earlier better, of course. But again, just don't feel bad about like having to suggest a late time if that's what works for you. Peer tutoring is available for all of our CIS classes in CERC 358. They also have an online schedule that I will be posting later this semester when it comes out. Okay. Expectations. Expectation is expected for your lectures and your labs. You're expected to go to this lecture and the lab that you are signed up for. It is not required because attendance is not technically graded in this class. But I will say there's a high correlation between the people who show up for class and the people who get A's in the class. And that's true for all of our classes. I understand if you have to miss sometimes, that's okay. Life gets in the way, same with being late, but you're expected to go come to class because the labs are useful time to get help on your homework, and the lectures are where I'll be going over in-class exercises. If you're not here to do the in-class exercise, yeah, you can totally do that on your own at home, but you're going to be missing out on the benefit of, being able to ask me questions live. Again, if you're sick, don't come to class, even if it's an exam day. If you're sick on exam day, email me before the exam actually occurs, so that I can know and we can figure out a time to make that up. An exam is supposed to be an accurate assessment of your abilities. I cannot accurately assess your abilities if you're sick. We'll try to make it up within a week. So again, just let me know. If it is sudden and you miss it and you can't inform me beforehand, I'll probably need documentation, like car accident, if that's the case, or if you're miss it because of hospitalization, I'll need documentation there, but letting me know beforehand is generally safe. Mental health. So if you experience significant stress or worry during the semester, changes in mood, problems eating or sleeping this semester, or whether because of this course or because of other courses, do not hesitate to reach out to me at any hour. I read those emails and I do respond to them. Everybody can benefit from from just having a person to listen to them. If you are having difficulties, the earlier you contact me, then the earlier I can come up with some kind of schedule or accommodation for you. This earlier I can suggest different services that are available on campus. The time to inform me about issues is not 2 weeks before the end of the semester. Unless of course that's when they're immediately occurring. But if you're having ongoing issues, the earlier you inform me about issues, or that there's just simply something impacting you, you don't even have to go into specifics. The sooner I can come in, I can, accommodate you, say, okay, I need these, we'll work on getting these assignments in then, and then we'll meet up next week to see where you are. Okay. Disabilities. If you have a need for an accommodation through DRS, then work through DRS. Email drs@temple.edu. Call them at their phone number. They're the ones to coordinate with if you need extended time on tests or a private place for testing. And they'll tell me what reasonable accommodations you need, or what accommodations you need. And as long as they're reasonable, I will make those accommodations. I have yet to meet an unreasonable accommodation, and doing these video lectures, recording these video lectures tends to knock most of those accommodations out as far as requirements are concerned. So obviously I'll be recording these lectures. You can make your own recordings of these lectures if that's what you need, like with a, audio recorder. But in this case, you do need to tell me Pennsylvania law is two-party consent. So you have to, you actually have to inform the person you're recording. The school's official policy is listed here. In other words, you can record it, but only for your personal use. In other words, don't sell it. So grading, this is the important bit. Grades will be curved at the end, but what the curve is, of course, depends on what the students get. Last semester, I think it was an 88.5 was an A minus as the cutoff. But the curve will only help you. An A is always getting a 90 or above will always get you an A. Getting an 80 or above will always get you a B. Getting a 70 above will always get you a C. Okay, so generally it's the curves affect who get them, like A minuses and B minuses and B pluses. And I'll explain that more later. The DFW, the getting a D and F or withdrawal from the course, and for similar courses around the US is consistently been around 30% for large classes. We were around 25% last class. Most of those were withdrawals. It's just students who said nope or I'm too busy this semester and just a W, and totally get that. D's occur when basically you turn in everything, but a lot of it's late and your exam scores are not that great. I generally do not award Fs unless you get an F by doing one of two things: cheating or not trying. If you try, you get a D at minimum. Okay, so it's weighted. So are your scores weighted accordingly? 10% for your solo exercises, 5% for your classroom exercises, your lab/demo assignments, which is your classical homework, that's 25%. Your final project is 10%. And then exams make up the remaining 50%. So half of it is stuff that you do in class, half of it is basically non-proctored stuff and homework, and the rest is, and half of it is exams. So let me go through that. We have three types of due dates, as I'll refer to them. We have soft due dates, firm due dates, and hard due dates, just like there's software, firmware, and hardware. So let's cover what I mean by these solo exercises and classroom exercises. This covers basically everything that is on Runestone, which I'll go into a bit. Basically, if it's part of your textbook, this is your solo exercises. These are short targeted exercises. The main complaint I had from last semester, which I'm trying to take into account this semester, is that there was a bit too much homework with regard, so I'm going to try to cut down on that. But basically reading the textbook, because it does keep track of what you read, as well as solving some of the problems in the textbook, that's what 10% of your grade is. These have soft due dates. In other words, they'll have a due date, which is when I want you to have it done. But as long as it gets done, it will get graded with no late penalty. Okay, so, but they have due dates as to where we want you to be at these points. This week I'll be adjusting that, but for the most part, assume that you need to read chapter 1. Okay. Same with the classroom exercises. These are also mostly from the textbook. They involve active learning. We'll be doing them in class, and they are intended to be fully completed in class. The answers will be given to you at the end of class, so there's no reason why you wouldn't be able to complete them. Okay. And you'll be able to work in the classmates and turn in the same exact code as your classmates, as long as all your names are on them for those. The way this typically works is that for these active learning exercises is that I'll introduce the exercise and it's broken up into segments. Then I'll give you 5 to 10 minutes to work on that segment, to brainstorm, not necessarily expecting you to get to an answer, but to make progress toward an answer. And then we'll come back and give you the answer for that segment. And then we'll move on to the next segment. So it builds on this. Again, same kind of thing for the due dates as those. So your lab assignments are the ones that are the most similar to homeworks in other classes. You get about 1 a week. They're intended to be started in and substantially worked on in the period they're introduced. They're supervised by me or the TA for the introduction. You can get help from your fellow students. It's highly encouraged that you work together with your students, and I will go into what is academically okay versus what is not academically okay in just a bit. And most important for the lab assignments, and this is the only requirement for, and this is the defining feature of the lab assignments. This is what needs to be demoed. This is what you need to, you have to show me and explain it to me or the TA to receive credit for these. The due dates are firm. They have a due date. It's 5 points late. Sorry, 5 points per day late. If you think about that, that's actually a fairly light penalty compared to a lot of other classes. And the maximum penalty is 50% of whatever of the points that are available. So any assignment can be turned in late for half credit. Late grades are determined when you turn it in, not when you demo it. But the sooner you demo it, the sooner we can tell you to go fix a mistake that you may have made or a misinterpretation you may have made. Because I don't really think that, like, if you make a reasonable misunderstanding, and that leads you to the wrong answer, I think that should be fixed rather than penalizing you. You have 2 weeks after the due date to demo your lab. Otherwise, we enter a 0, but this can be waived. Now, the reason I have this in is because, again, I did not know we had to demo our labs clause at the beginning of the syllabus. This is so that I can say no to a student who did not demo all of their labs all semester, because that generally ends up being a really painful experience for everybody involved, both me and the student, as they struggle to run code that they can't figure out why it isn't running because they haven't done it all semester and probably just cobbled it together at the last minute. So, but in general, if you're like, if it's 3 weeks after the due date and you realize, oh, I didn't demo that, just reach out to me. We'll waive it. It's fine. This clause exists so that I don't have to deal with just the giant demo, a mega demo, as I call it, at the end of the semester. They're awful. Okay, again, turning in your lab assignment, submit it online to Canvas, and then demo it to me or your TA. We may ask you a question. Sometimes it may be detailed as what was your strategy for solving this problem, and sometimes it may be as simple as what was the most difficult thing for you on this problem. Okay. It's also important to let me know if you're struggling to finish a lab by the due date, because if you're struggling, you're probably not the only one who's struggling with it. So the more people who let me know, the better indicator that gives me that I might have to give an extension to everybody. Okay. It also gives me a indication that maybe I should go over that topic in the lecture. So I've been known to do that. If people are struggling with one specific problem or subproblem, I'll go over it in lecture. Okay, so the final part of this course is a final project. I know that's weird, getting a final project in an introductory class. Now, this don't feel too stressed about this one. It's really not. It is the vast majority of students get a 90 on this. It is an opportunity to take your skills in programming and develop your very own piece of software. Essentially, my intention here is to take you, throw you into the deep end of the pool and show you that you do in fact know how to swim. I want to give you the chance to learn something new that you would not normally have the chance to do. So I'm sure there's a lot of you who love video games. I mean, I love video games, right? I really love video games. I'm a huge fan of the Dark Souls series. I love 4X games, like Stellaris and Europa Universalis 4. I enjoy a lot of different video games. I'm a big fan of Mario, Mega Man. I play a lot of video games. And one thing I really didn't get much of an opportunity to do in my undergraduate degree was make them. And this is, if you're interested in making your own video games, this is the excuse you need to learn it for credit. So to experiment with an engine like Unreal or Godot. There's something special about student projects and student-made games because we get to see a lot of passion for them. We get to see a lot of passion that's, a lot of quirky things. A lot of students end up making visual novels in Ren'Py because that's a Python-based engine for making stuff. So they make choose your own adventure, and then they break the engine and make mini games within. So they make games within games. It's pretty cool. A lot of seniors opt to take to double dip, as I explained, which is they apply programming to whatever senior level class in their major they're doing, and thus basically do the same project in 2 classes, but they get to apply programming to it. Some students build hardware, some students do websites. So it's really open-ended. It's a lot of fun, and is a great learning experience for everyone. You can do it in any language you want. You can use whatever infrastructure, and you can optionally do it as a team. It is not required to do it as a team. And team projects, a lot of people, have various experiences. Some people love them, some people hate them. But you can choose to work in a group of 1, 2, or 3. It will be divided into 4 stages. Brainstorming, proposal, progress report, and final project. I'll go over those later on. But the final project will be due at the last day of class, the very last day of class. So that very last Monday before our study days. This and the exams are the only hard due dates. Okay. The due date will not be altered unless you have like a sudden or documented emergency, such as I was on a flight and my flight got delayed by 3 hours and I can't get home to hit the submit button, which happened. It's a hard due date. Late submissions here are penalized at the rate of 0.1% per minute over the listed due date. So an hour late is 6 points off. But the idea here is that whatever you have, turn it in. Whatever you have, just turn it in, please. Don't be intimidated by the scope of the project. We are far more interested in the journey, not the destination. It's meant to be a learning experience, not a tech startup. The only thing I do want to mention is that there's this idea of proposal where you have to tell me what you're going to do. And if you do not have a proposal by the time the progress report is due, and the progress report is due like a week before the actual due date. So in other words, if you don't have a proposal by the time there's a week left, I'm just going to write in 0 and save us all the trouble, because it never turns out well. You will be too far behind to catch up. I will remind people multiple times. I'll have an entire day dedicated, which I call proposal day, where basically everybody just simply gets on Zoom and just pitches me their proposal, and I will okay it. Okay. You are allowed and encouraged to do the same final project in this course and another course your group member is currently taking. The only requirement is you get the emailed consent of the instructor in each course. Okay. So exams will occur most likely during week 6 and week 10 or 11. They will be on paper. They'll be administered in lab. It's just simply easier for security reasons to do it on paper. There's just too many tools these days for assisting with programming. Plus, doing it on paper means I can actually ask you questions like, what does this code do? Which is extremely useful because if I try asking you that on a computer, you could just run the code. And so this broadens the range of questions that we have. Again, the due date for the exams is hard. So again, and the final exam is the same. So the first 2 exams are worth 15% each. The final exam is worth 20%. Exams mostly, again, will occur during week 6 and week 10 or 11, and they'll be given in your lab period. So you'll have that entire hour and 50 minutes to work on it. Okay. As far as what what notes will be allowed, we'll be discussing that at a later date. I'll probably allow you a cheat sheet for that. But really it's not necessary. All right. So I'm going to discuss academic honesty policies here, just so you understand what's reasonable versus what's not reasonable, because honestly, a lot of classes don't give examples of that. And then I'll show you your textbook. Okay. So I'm adapting CS50's academic honesty policy. CS50 is an open source computer science course that Harvard does. I liked what they had, so I took their examples, added to it, and took their verbiage and added to it. Be reasonable. That's their policy. Your interactions with classmates and others facilitate mastery of the material. I believe the only way to truly master it is to be able to teach it to somebody, and that's part of being able to work with people. There is a line between getting help from a person and submitting that person's work as your own. So I'm just hoping to kind of define this. So the essence is that all the work you submit on non-group assignments and exams have to be your own, but collaboration is encouraged so long as it's not basically somebody else doing your work for you. So the general rule, when asking for help, you may show your code to others, but you may not view but if somebody has a working solution, you may not view their code. So basically, if you need help, feel free to say, I am trying to run this code. You can say on Discord, hey, I'm trying to run this code. It's not working. Paste. Can anybody else, can anybody figure out why? And that's perfectly fine. That kind of thing is not only acceptable, but encouraged. If you are having trouble completing an assignment, please send me an email so I can arrange to walk you towards an answer. Don't go to Chegg unless you want to fail the course and receive an academic misconduct charge. Don't go to ChatGPT, as tempting as that is, because it might spit you back a solution you don't really understand, and that's not going to help you on a final exam. Please,
I have a question.
Contact me. That's your job. My job is as an instructor. Yes.
So can we have help with from other people that are outside of this class or no?
Yes, you can. I will
Okay,
go over,
thank you.
I'm about to go over specific examples, and that is one of them. Yes, you can get help from people outside of this class. In fact, you will probably get help from people outside of this class if you go and paste it on and go and ask for help on Discord, because it's not just for this class, but for a bunch of other classes I teach. So what's reasonable? Communicating with classmates about the assignment or to understand the material, helping somebody identify a bug in their code by viewing, compiling, or running their code even on your own computer. Sending or showing code you've written to somebody else, possibly a classmate, so that they can help you identify a word, identify and fix a bug, provided you cite the help. E.g., I worked with Alice Awesomeface. Incorporating a few lines of code that you find online or elsewhere into your own, provided those lines themselves are not the solution to the assigned problem. So basically, it's like, oh, if I need to print out if my task is to print out all the print out like all these numbers except for these numbers, and I get something that does exactly that from online, you didn't do it. So in that case, but regardless, what I want you to do is that I want you to cite. Citing here is, you don't need to worry about MLA or anything like that. Just simply give me the URL where you found it and leave it in what we call a comment. You're going to learn what a comment is in a few days. But basically, that's just a line in your code that your computer does not read, but humans do. So an example, looking up how to print out the contents of a dictionary in numerical order on Stack Overflow as part of a larger lab, copying the 1 to 3 lines of that and citing a link to Stack Overflow, that's perfectly fine. Generally speaking, if you cited it, I'm not really going to be bothered by it. Okay. Sharing a few lines of code online so that other people can help you. Posting it on Reddit, in other words, asking for help. Turning to the web or elsewhere for instruction beyond this course's own, for references, such as like the material I listed, or for solutions, but not out to technical difficulties, but not outright solutions to our exercises or your final project. In other words, if you're saying like, how do I get for instance, suppose you're working on a program, and part of that program requires you to turn the background yellow, trying to figure out how to turn that background yellow or how to change color in general, that's the kind of thing that's appropriate to Google. Whiteboarding solutions to problem sets using diagrams or pseudocode, but not actual code, working with and even paying a tutor to help you, provided the tutor does not do that work for you. So what's not reasonable? Accessing a solution to some problem prior to submitting your own. So, getting somebody else's work, asking a classmate to see their solution before submitting your own, failing to cite the origins of a code that you discover, of some code or techniques that you discover outside of class. For example, copying and pasting code from an on-site, you find from a site online will be trivially identified. Finding code online that addresses a question on an exam and failing to cite it would violate this policy. Finding code online that you think might address the question at hand and blindly copying it into the exam when it doesn't actually address the question is a great way to annoy me. I don't generally appreciate it when people just try to write, they look at a problem, have no idea, and they just try to write gibberish. I'd rather you write pseudocode. In other words, English explaining the problem solving process, because I can give partial credit for that, even if you can't write the code. Giving or showing to a classmate the solution to a problem when it is he or she and not you who's struggling to solve it. Paying somebody else to actually do the work for you. Searching for or outright soliciting solutions. An example is like looking up an answer on Chegg. If you find my questions verbatim on a source like Chegg, it's best to just simply ignore it, because I guarantee you I have a copy of those. I've had students say they look up how other people to do that problem and just create their own solutions. That's just cheating with extra steps, because the unique solutions invariably look identical to the solutions that they found online, and you learn nothing except for what it looks like when I'm angry. The cheating is really the only thing that makes me angry. Again, when in doubt, if you're having issues like going from part A to part B, or just even figuring out what the separate parts are, email me. It's my job to help you. Splitting up the workload and saying like you do parts A, B, and C, and they do parts D, E, and F, and then combining your answers. So I think you've all got the idea. That being said, I do have something called the regret clause. If you violate if you do something that's academically dishonest, say, example from last semester, you look at somebody else's answer while you're taking the exam and you realize, I just did something kind of not great. And you come to me within 72 hours, I will not make it an academic dishonesty charge. I will just simply, probably, in that case, for that student, I just simply gave them I appreciated them coming forward. I gave them a different question to do instead of that question. For other students who have done that, depending on the circumstances, I just simply take a 0 on that question that they cheated on, or on that assignment. But it's not an academic dishonesty charge, which that's just not great. All right, disclaimer. It's subject to change. You have rights. They're linked here. All right, so let me go ahead and show you your textbook. Your textbook is fairly awesome. It's this is Runestone. It's got a bunch of other textbooks. I have an account. What you'll want to do is that you'll want to sign up for a course. So, you'll go to login or register, and it'll have this page that says sign, and you'll want to hit this button eventually, sign up. And you'll eventually be taken to a page like this. Your username can be whatever you want. Your first name and last name should match what's on Canvas, just to help my script out, because it's a separate grade book. That's why. And so I have to import it into Canvas. Your email should be your TU email, because in case something is messed up with your name on Canvas. Obviously, I don't need to know your password. But what you put here for the course name is Spring 2024 Rosen, and that will bring you to the textbook. You do not need to make your own course. Also, making your own course won't give you the answers to the problems. It will let you see the code that runs in the background, which is pretty cool. But the way a lot of the answers are graded are via unit tests, and that's just simply trying to figure out Python answers by learning more Python, which is, sure. So anyway, once I'm logged in, I hit login, and here I am. So I have all these assignments. I have the assignments out. I need to modify the due dates for some of them. But the ones on the bottom are the ones we need first. I'll probably disable the other ones so you can see them better. But again, we want you to read the chapter 1 readings and the chapter 1 exercises. Chapter 1 readings, do assignment, and then it will tell you these things. You read it, mark as completed. Generally says you did 1 or 2 of the activities on the page. Guess what the other activity is? It's playing the video. So interact with the things, as you go through. The examples are there to help you. This demonstrates one of the cool features of this textbook, which is that, and why I use an electronic text, you can run the code in your textbook. rather than having to try to type it out on your own editor to see what it work or your own computer to see how it works. So here, enter the radius 5, and it runs and gives me the area of the circle with radius 5 is 78.53, and then a bunch of digits over there. We'll learn a bit why as to why that happens, but that's okay. And then also you can download the code and run it on your own computer if that's what you want to do instead. But this has a built-in editor, which is pretty awesome. Same thing for the exercises. The exercises generally will be able to tell you, okay, they're multiple choice things. And if you get it wrong, it gives you the chance to keep doing it until you get it right. I don't find like the standard way math homework works, which is you turn in the answer, you get it right or wrong, and then that's it. Because if it's right or wrong, there's just very little incentive for you to go back and fix it. Here, I mean, it's telling you whether it's right or wrong. Again, this stuff is, talk about this all you want on Discord and stuff for help with this. But generally though, to find the textbook itself, the actual pages of it, that's just simply the list of assignments. You click here, Foundation of Python Programming. And it will keep track of like where you are in the textbook and that kind of stuff. You can also find the assignments just by clicking on this person icon and going here. And these are for, again, these ones, the soft due date. It's a very good textbook. We'll go through mostly in order up through, I think, we'll go through part 5. We'll make a little bit of a jump very briefly to the functions, just to teach you how functions work. But for the most part, our first exam goes through what is called iteration or for loops. So through chapter 7. That's what we expect you to know for the first exam. Now, if you're having trouble getting Python working at some point, or you don't have access to your normal computer, as long as you have access to a computer, you can get to this website and you can code. Notice next to this person icon is this scratch board. You can use this area to just write whatever code you want. And so I can write a fully working Python program right here. I can type print hello, comma, world. And hit save and run. And there it prints out just now, another cool feature is that it does automatically keep track of your changes. Notice when I hit save and run, this updated over here. And so you can rewind to your previous attempts. So don't worry about like, keeping track of your versions in here. It's automatically going to do that for you. It's very nice. It's a very useful feature. There are a few exercises that have some weird quirks to them, and I try to give a heads up about them. I'll probably try to modify them this semester so that students don't have to deal with them. But just let me know if you're having if you spend more than 15 minutes on an exercise. That's not what I intend, so please let me know. The other thing to note is that over here in the textbook, if we scroll all the way to the bottom, well, not all the way to the bottom, if we go all the way to the bottom, it has the copyright notice, which is this Creative Commons, and we have the project list. This is why I really like the textbook. These are projects, these are the in-class exercises we'll be doing. And these are fairly good exercises. On Thursday, I plan on doing this one called a preview of the end goal, which doesn't require any coding knowledge, but we'll be running code. Is that a question? And seeing the kind of things you would be able to do by the end of the semester. I also am a fan of introducing topics multiple times as though it's the first time you've seen it. So we'll be introduced to the concept of turtles and turtle graphics quite a bit. Turtle graphics are basically a very easy way for us to do graphics that are built into Python. And that's why I was talking about the coordinate plane, this entire canvas that this turtle is painting on, and we'll understand that concept a bit later. This is 0, 0 on an XY coordinate plane. So that's what I mean by it being a bit, about needing a Euclidean plane. All right. So any questions before I move on to talking about what actually we are in?
I have another question. It's
Sure.
about the demos. So how do you want us to submit the demos? Do we show you the code and explain it in person, or do we show a video?
In person or over Zoom is the demo. You can do the demo in person during the lab or office hours, or you can arrange a time over Zoom to show it.
Okay.
But the most convenient time will most likely be during lab.
Okay, I got you.
Again, and this stuff doesn't need to be demoed. The first lab on Friday and Monday respectively will be a very good example. It's mainly there to get you set up with Python, show you the workflow for that we have for assignments. You know, the whole and kind of get you acclimated to the demoing process. So, and also, as far you may have noticed that we didn't have class and therefore lab on Monday. Think of this class as starting on Tuesday, so it will be lecture, lab for each week. So so week 2 starts next Tuesday for us. So when I say that we'll be having our exam on week 6, that means the 6th Friday and the 6th Monday of the semester. Yes. It said it was invalid. I will fix that tonight. I'm sorry. I did not. It's invalid, really. I thought that was the new one. Okay, I will fix that tonight. I'm not on my normal computer, so I will fix that. Yes. This one or the one on the syllabus worked. Okay. Awesome. So the one on the syllabus worked. I have a suspicion as to why it didn't work. Hold on a second. Okay, that's not, so my suspicion was wrong. And so Discord linked. I thought that's the same one. Copy. Nope. Copy link. And then edit. Possible I just simply dropped the letter or something. Also, your TAs have let me know what their office hours are, so I will be updating that for you. I feel like that's the same. Go ahead and try it again. All right. One other thing with the lecture recordings, by the way, while I'm here, you will find the lecture recordings not just for this. Your lecture recordings will be here, but I also have all the lecture recordings for all the previous semesters. So if you find that that one isn't to your taste, or you need it explained a different way, you can find it. And you have an entire plethora of playlists. Okay. So with that being said, any other questions? All right, so here, what we're going to do now is that I'm going to go to my GitHub. Because again, I have my, because again, I'm not working on my normal computer. Intro. And lecture 1. It's one I've been using for a while. It's not pertinent for this class, but hey, or rather, it's not fully pertinent, but it works. Yes. Uh-huh. Interesting. That this isn't set up. Okay. We're setting. Interesting. Show me after class if you don't mind. Okay. Is that okay? All right. Yeah, because I want to if there's an issue, I want to fix it. Okay. So first off, things I want to talk about are just kind of a brief overview of what is computer science and the history of computer science. Because it's got a bit of a wrong name, because it's kind of the equivalent of calling biology microscope science or astronomy telescope science. It's the tool we use. It's not, and science isn't really about the tool we use. Science is a tool we use to be, to use a phrase I really don't like, but is very good, less wrong about the world around us. It gets us towards a closer truth. So computer science is not the study of computers. It's not programming in itself. I thought computer science was programming when I joined, a computer science program, but that's not in fact what it is, but it is an important part of programming. And it's existed for longer than computers have, and various components of it have their basis in mathematics. I really enjoy, so if you ask a bunch of computer scientists, they'll probably all give you the same, a different answer as to what is computer science. The authors Gibbs and Tucker, I really liked that their definition is that computer science is the study of algorithms. I think that's a not wrong definition. It is a science. It's the study of how we can automate problem-solving processes. It asks, what can, when we get right down to it, actually be automated? And then it also asks, how can we efficiently automate something? Theoretical computer science, and this is a quote here, covers a wide variety of topics, including algorithms, data structures, computational complexity, parallel and distributed computation, probabilistic computation, quantum computation, automata theory, information theory, cryptography, program semantics and verification, machine learning, computational biology, computational economics, computational geometry, and computational number theory and algebra. Work in this field is often distinguished by its emphasis on mathematical technique and rigor. Okay, it was a long paragraph. So what does it mean that when we say computer science is the study of algorithms? Gibbs and Tucker further define, who's a textbooks I used to use for Java when the intro program was in Java. They say that computer science is studying the behavior of algorithms to determine if algorithms are correct and efficient. And also I noticed that I haven't defined algorithm yet. We'll get there. It's designing and building computer systems that are able to execute these algorithms, designing programming languages and translating algorithms into these languages so that they can be executed by the hardware. So in other words, we've got to have a computer. We've got to have the thoughts in our head as to how to solve a problem. And we got to put these thoughts in our head into a language that the computer can understand. And then finally, identifying the important problems that can be solved by doing this. Now, as far as languages have been concerned, Python is one of the more recent ones. I think it was 90s they came out, and it's known for being very concise as a programming language and very simple to use. And one of the reasons I like it is that when I teach Java, if I'm teaching Java as the first programming language, there's a lot of stuff I have to say that, like, this is the magic words you have to say at the start of a program to get a program to work. Ignore them for now. Just know that you have to put them at the start of a program. You'll understand what they mean by the end of the semester. And that always feels a bit off. And in Python, you'll understand what you're typing as you type it, which is great. So as far as languages, there are some languages that are harder and some languages that are easier. Python is one of those that I find to be easy. So what can you do with a computer science degree? Obviously, you can do software engineering. And it demonstrates essentially that you know two things. You know how to program and you can design solutions to problems. I like to think of computer science or a degree in computer science or its related fields as a degree in problem solving. But a lot of you aren't computer scientists, so I should probably talk more about interdisciplinary stuff. So if you're in biology, chemistry, or medicine, bioinformatics, that is biology and computer science combined. It is big right now. It is basically, it was big before COVID. It has been bigger since after COVID. It is basically about trying to automate a lot of processes, like figuring out the ways proteins fold, or figuring out new different, or simulating ways drugs can interact with viruses, to, you know, make sure you can have a probable workable solution before you try to do testing. So cancer detection and design of new medicines, designing HIV inhibitors. Fun one that also gets thrown under there with also combination engineering is prosthetics. The ability to, the more advanced the prosthetics are, the more electronics and programming it's going to need. There have been essentially artificial eyes that people that if I recall what I've read correctly, that partially work on stuff. So there's a lot on there, and prosthetics have made like huge leaps and bounds. Physics and astronomy. I mean, quantum computing's all the rage right now, and that's requires, knowledge of quantum physics and stuff, but that's something that's really cool these days and really hot in physics. Supernova detection. Most of the supernovas that are detected these days are done so automatically by telescopes. The Large Synoptic Survey Telescope, and when I wrote this about a decade ago, is expected to gather about 140 terabytes a day. Somebody's got to go through and analyze all that data. Works well with engineering here. Computational engineering is its own thing in low level. Business and economics. Knowing how to do, there's a lot of strategies about team management that occur in software development. And of course, if you're really into money, high-speed trading algorithms. That's where the money's at. And I do mean the money, not the work for Google money. I'm talking about the work for banks and make lots of money. Psychology. There's a whole field dedicated to this called human-computer interaction. That's the whole about how do humans actually use computers and the interfaces around them. What is good, what is useful, what hurts eyes. So what should we use, what shouldn't we use? That's the kind of the good side of it, making computers easier to use for people, making interfaces simpler, making them more intuitive. The darker side of it is, of course, how do I keep people on my website for longer so I can rake in all that juicy ad revenue? But that's still a good knowledge to have. I got my start in undergraduate research and thus my getting bumped into grad school by doing stuff in an HCI lab, a human computer interaction lab in the psychology department. And that was all about different ways that we could make better user interfaces for the visually impaired community. Education and educational resources. Used to be a whole ton of games that were educational when I was a kid, but like using computers to make education better is its own thing. I mean, we're using that right now with an electronic textbook. So with that, so now that we've talked about what we can do with computer science and other fields, what is an algorithm? So the word algorithm comes from the Latinized name of a Persian mathematician, Muhammad ibn Musa al-Khwarizmi. His Latinized name is Algorithmi. So that's where we get his name. We can go ahead and look him up on Wikipedia and it will come up. He's one of the, so birth 750 to 850, Persian polymath. He was around the, I think the Arabic Golden Age, Islamic Golden Age, where there was a huge just boom of arts and sciences in that part of the world. We get a lot of the Portuguese term algoritmo, meaning digit. He was pretty important as far as mathematics were concerned, because he wrote a textbook in 820 called The Concise Book of Calculation by Reduction. What happened is that he noticed that there were these new, extremely useful and easy to use digits, a base 10 system coming from India. And he's like, this is way better to do mathematics in than what I'm currently using. So it was a precursor for what we use today, as far as our numerical system is. So he wrote a book on that. And we get the word algebra from algeber, the first word of the name of his textbook. So he gave formal instructions on how to do these mathematical operations in this relatively new Indian decimal system. It got translated into Latin in the 1100s, and then it spread throughout those places of learning in Europe. And so his Latinized name again was Algramidi. So the word algorithm comes from him. Algorithm is a set of, so the formal definition for algorithm is a set of well-ordered, unambiguous operations that yield some result in a finite amount of time. That's a lot. It's a lot of words. So let's break that down. And that's how we do a lot of problems in computer science. If you've got something that's big, break it down into small parts. Okay, a set, a group of well-ordered. So well-ordered means it has a specific order, like a recipe. In fact, think of algorithms like recipes. You don't put the ingredients into an oven when you're baking bread and then take it out of the oven and then mix it. You got to mix the ingredients first, do a bunch of stuff to it, then put it in the oven, then take it out at the exact right time. Baking is a science. Cooking is an art. Baking is a science. So well-ordered. There's a specific order into which to do things. Unambiguous operations. Operations are just things you do. Unambiguous means there's no way to misinterpret what we're doing here. Okay, so well-ordered. So operations can't misinterpret what they're doing. They occur in a certain order, and they yield some result in a finite amount of time. It actually does something, is what I'm saying. It does something, and it's not going to go on forever. That's what an algorithm is. You've been doing algorithms for as long as you've been doing mathematics, be it the algorithm for doing addition and multiplication by hand. So when you add a bunch of numbers together and do the whole carry the one thing, or you multiply two numbers together and do it by hand, or you do long division, those are algorithms. Those are sets of operations that you have to do in a specific order. Think of addition. With addition, in order for the algorithm as written to work, you have to go from the ones place all the way to the largest place. You can't go from the largest place to the smallest place. Otherwise, you have to like back up and redo stuff. Algorithms, once we turn them into algorithms are what we turn into programs, and they allow computers to automate various tasks. Okay. This was more relevant for other stuff that I used to go on. But so with the last time I have here, I want to go over a very brief history of computer science, very brief history of how this field developed. The first kind of computational aid that humans developed, as far as we know, is the abacus and its various variations. That was not a computer. The human was still the computer then. In fact, computer used to be the title for a job. It was not a computer. It was just data storage, but it allowed humans to basically do their computations better. We didn't really have much maybe on paper to do computations until gear machines started getting proposed by various scientists and engineers between the 1600s and the 1800s. The idea here was that these gears could turn in some automatic process, and the position of the gears would indicate what numbers were being used, right? So you could label the gears, and if they came up a certain way, if that was what the number was. This was proposed by a number of people that you might recognize from various physics or science lessons, Pascal, Leibniz, and Babbage. Babbage, though, probably not, because he's really only recognizable in computer science. Babbage specifically wanted to create a gear-based machine which could print output onto paper, which was much more useful than just kind of, having a machine turn and then manually figuring out what the answer was from the position of the gears. That brings us to the first computer scientist who we commonly refer to as the first computer scientist. I've yet to hear a better proposal than this person. Augusta Ada King, the Countess of Lovelace, often referred to as Ada Lovelace. Those of you, and for those of you from the English department, née Byron. She was Lord Byron's daughter. Byron was quite the figure. He he's got the Byronic hero archetype named after him. He was a renowned author, and he was as much of a celebrity, and he was a celebrity back then. And he led, as far as I understand, quite the scandalous lifestyle. His divorce was so outrageous that people were still arguing about it after both him and his wife were dead. It was quite, so he was quite the figure. So Ada's mother was like, yeah, the arts don't seem like a good place for you with your Byron blood. Let's throw you at the sciences. So Ada Lovelace got quite the background in the sciences. And she eventually got introduced to Charles Babbage. And what she did is that Charles Babbage never managed to create his analytical engine. He designed it, but never made it. But it was a theoretical machine. Had it been implemented, it would work, you know. And what she did is that she took a paper that was being that somebody else had written for it, translated it, and then added her own notes to it to expand the paper. Right. So she translated these notes on the paper about this, added her notes to it, and added a working program at the bottom of it in her notes, saying that these, if you follow these instructions, do these, and do these instructions, you could compute Bernoulli numbers, which are important in probability and statistics and combinatorics and that kind of field. Also worthwhile, but what makes it really special is the fact she wrote about how to use a machine like this for doing stuff other than numbers, for doing operations and stuff other than numbers, which was about 100 years out of its time. Sadly, if we look her up, she died at quite the early age, I think in her early 30s. Age 36. So she died, I believe, of pancreatic cancer. But if you're interested, she translated an article by engineering Luigi Menabrea, who was later the Prime Minister of Italy, about the analytical engine, and supplemented it with an elaborate set of 7 notes, simply calling them notes, which you can read here on Wikisource. And as you can see, she's got quite the bit of mathematics in there. So the next kind of big jump for computation, though, was basically necessitated through cryptography and cryptanalysis. Cryptography and cryptanalysis, code making, code breaking. Up before World War II, you could essentially, still decode even the most advanced ciphers by hand. Decode enemy orders. This would give you an information intelligence advantage, right? If you know that the orders say attack this unfortified position at dawn, you could either unfortify this position, you could either fortify that position, or you could just simply move your troops away so that you would suffer no casualties and retreat to more. So that kind of information and getting that information was exceptionally important. The birth of modern cryptography was essentially World War II with the various mechanical designs for doing encryption, the Enigma machine primarily. Intelligence known at the intelligence that we got from being able to decrypt that, or the Allies were able to decrypt that was referred to as ultra. Anything from the Japanese theater was called magic. So if you had ultra magic clearance, you were pretty important. Alan Turing led the effort at Bletchley Park to do the decryption. He's commonly referred to as the father of computer science. He designed various techniques for being able to decrypt the German ciphers. Partially, this was because of use of what are called CRIDs, where you know what the output is supposed to, you intercept a message that's encoded and you know what the answer is supposed to be. And if you can decode that, you know what you can decode all the other messages you intercepted. For instance, weather station out in the deserts of North Africa, that's not really involved in the war, saying no action today, nothing to report. That, also Germans were very fond of signing pretty much everything with Heil Hitler. So knowing where that was in the crib also gave you a way to, analyze that. And since you know what that output was, if your bomb produced that, you were able to figure that out. And then you could intercept the German U-boats and know where they were. And your planes could get miraculously lucky and find them and shoot down those U-boats. Or you could move your shipping, your various naval vessels out of the way of those U-boats. Eisenhower said that Ultra was decisive to an Allied victory. And the estimation is that it lowered World War II's length by about 2 years. So Alan Turing is again probably one of the more famous computer scientists. Sadly, he also died at an early age because because he was a gay man at a time when it was illegal to be homosexual in Britain. He was given when it came out publicly that he was indeed a homosexual, he was given the choice between imprisonment or chemical castration. He chose the latter and then committed suicide soon after. The government of Britain made an apology for his death, basically in the past decade, I think. But besides his code breaking, was also his work on the Turing machine, basically the formal mathematical model of what a computer is. And because you had a mathematical model for it, you could prove mathematically what computers can and cannot do. This gets into a high-level class called automata theory that we have at Temple that we teach. So if you want to learn about that, you have to take automata theory because it gets into the high-level math. As far as the first computer, there's no clear first. Some textbooks say it's ENIAC, which looked like this. Huge computer used for artillery calculations. There's no clear first, but there's a lot of contenders, and they were all massive and big and used and required vacuum tubes and just awful amounts of just space and heat and energy. One of the first people who worked on those was Vice Admiral Grace Hopper. If you've heard the term computer bug, she came up with it because she discovered a literal bug in a computer that was causing issues. And thus, that's where the term comes from. But she's important for a lot more reasons than that, and I don't have the time to give her justice. So you should read up on her. Hint, hint, because your first assignment asks you to write a biography of a famous computer scientist. That would be a good one. IBM introduced its first personal computer, PC, in 1981. Personal computer, because you could actually take it out of the building and, put it under a desk and use it. So at that point, computers became household instruments you could use. The next big step in that has been there's been basically two big themes ever since then. Network connectivity. Basically, the computers are nowadays all connected to a giant network of computers. There's a World Wide Web, which is an application that runs on top of the internet that we use to basically to go to visit websites and look at cat memes all day. And honestly, there's not a better use of it. The web is so large, it requires search engines to find what exists. The other thing is that, computers have gotten smaller and smaller and smaller as the years have gone on. So with the last bit I have, I want to say is that there's two pieces of advice I have. The only way you're going to be able to succeed in this class is by practicing. We're going to start, and again, this first lecture will help that we do on Thursday will help with that. And the other thing is do more work so you can be lazy. It's weird to phrase that, but the idea here is that the idea behind programming is you can put in quite a bit of work for a very repetitive task, and then you never have to do that repetitive task again. It's being willing to put in this initial work So you can be lazy later. All right, with that, I believe there was a technical issue, so if you could show that to me, I'd be grateful. If you have questions, please come up here. I am basically have to leave at 4 p.m., so I am open to speak with people until then. Stop share, stop record.